A classic problem about the mean value theorem that's often asked in calculus courses, well, that classic problem goes like this. Given a function f and points a and b, I want to find some other point c so that f prime of c is equal to f of b minus f of a all over b minus a. The mean value theorem promises us that as long as f is a nice enough function, nice enough meaning it's differentiable on the open interval ab, continuous on the closed interval ab, that as long as f is a nice enough function, then that's possible. I can find that point c so that the derivative of f at the point c is equal to f of b minus f of a over b minus a. Well, let's do an example where I try to find that point c. So let's do an example. I'll have f of x, I'm just making up some example, it'll be x cubed, and it'll be on the interval where a equals 1 and b equals 4. So really, what I'm trying to do is find some point c so that the derivative of the function at the point c is f of b minus f of a over b minus a. Now in this case, f of b is 4 cubed, that's 64. F of a is 1 cubed, that's 1, and b minus a, that's 4 minus 1. This is 63 over 3, that's 21. So I'm looking for a point c where the derivative is equal to 21. Now can I do that? Yeah, I just got to differentiate this function. So here we go. I'll differentiate this function and I get that the derivative of x cubed is 3x squared, and I'm looking for which value of x is that equal to 21. Well, I'll divide both sides by 3. I'm looking for a value of x where x squared is 7. So divide both sides by 3. And my x should be between a and b, right? So in that case, x is the positive square root of 7. And what I've really accomplished here, if I make a little graph, here's the xy plane, and I'll draw kind of a made-up graph of the cubed function. Right, here's the point 1, say, here's the point 4, here's 1 comma 1, here's 4 comma 64, right? The slope of the line here, right, is 21. All right, the slope here is 21. And what I've really managed to do here is find that at the square root of 7, the slope of the tangent line is exactly the same as the slope of the line through 1, 1 and 4 comma 4 cubed. It's super important to emphasize that although these kinds of problems are fun, and the mean value theorem guarantees that for nice enough functions we can find such a c, yeah, these are fun problems, the mean value theorem guarantees that it's possible, but that's not the point of the mean value theorem. The mean value theorem is more than just a computational result. It's really an existence theorem. It's important to emphasize the power of these existence results. Something like the mean value theorem tells you that something exists without you having to actually go out into the world and find that thing, right? And having you do a ton of problems where you find the point c really would undermine that important lesson, right? The power of the mean value theorem lies not in the fact that you can actually go out and compute the value c, right? The power lies in the fact that the mean value theorem tells you that it's possible, that you know there's a value of c out there without you having to actually go and find it. And because of that, it opens up the door to all these interesting conceptual applications where we're relating, say, positive derivative on an interval to the fact the function's values are increasing. And that's really the power of the mean value theorem. It's a conceptual result that lets you relate information about the derivative to information about the original function.